I want to talk today about two aspects of regularity theory for singular and degenerate PDEs. On the one hand, qualitative results, on the other hand, quantitative results or sharp estimates. And let me start by saying a few words about why we want to study this type of PDEs. The first reason is because we cannot avoid this type of equations because they appear in many applied problems. So they are unavoidable if you want to understand certain phenomena. Apart from that, they are very interesting objects from the point of view of analysis, because you want to understand what can you save in terms of regularity for the weak solutions when the crucial algebraic assumption of ellipticity, say, collapses in the PDE. So the techniques that we know to obtain regularity, they are based on deriving analytical estimates from algebraic assumptions, and the most well-known is ellipticity. So when ellipticity collapses, when the modulus of ellipticity becomes 0 or infinity, can you still obtain regularity results for the weak solutions? And this is a very interesting problem in analysis. And in fact, the answer to this is yes. And we're going to try to understand why we can do it and what type of results we are still capable of obtaining. But let me start with some examples of singular and degenerate equations. So the typical singular and degenerate PDE is the P Laplacian, which appears here in the first example, both in the, say, elliptic and the parabolic case. And the equation is degenerate when P is greater than 2, because at points where the gradient is 0, the modulus of ellipticity vanishes. And for P less than 2, the modulus of ellipticity blows up at points where the gradient is 0. So we say that the equation is singular. Of course, the case P equals 2 is the case of the Laplacian. The P Laplace equation appears in the minimization of the P energy and finds applications, for example, in the modeling of non-Newtonian fluids involving power laws, in the modeling of the collapse of sand piles, where you have a typically slow diffusion, fast diffusion phenomenon, because you see when P is, say, large, at the points where the gradient is above 1, the diffusion coefficient is very, very large. And when the gradient is less than 1, the diffusion coefficient becomes very small. So you have this situation if you start from an unstable configuration in which the gradient is larger than 1, then a kind of avalanche starts, and then the gradient starts diminishing, and when it crosses the threshold and becomes less than 1, then diffusion slows and you converge to a stable situation, right? So the P Laplace equation is very useful in this type of modeling of sand piles. A recent, very interesting application, I mean, these equations keep appearing in different contexts, and recently, you know, a lot of people are studying machine learning, and the P Laplace equation appeared in an area which is called semi-supervised learning, when you have a large data set and you have a small subset of data where you have labels. and you want to extend this labeling to the old data set. Okay, so if you want to do this, I mean, this is obviously an ill-posed problem, because there are many ways of extending the labeling to the old data set. So you have to introduce some regularity in the problem, right, in order for the problem to be well posed. And what people were doing typically was to use the so-called Laplacian regularization. So you consider a weighted graph where the vertices are the points in your data set, so for which a certain subset is labeled. So this corresponds typically to the boundary conditions that you have, okay? And then you want to extend this. And this L2 regularization, so you introduce some smoothness into the problem by trying to minimize the square of the distance between your learned function in different points. So what happens if you do this, what you observe is that the minimizer corresponds to a surface which is almost flat and has spikes at the labeled points, right? If your subset of labeled data is very small compared to the old data set. If you replace the 2 by the p, you see that in fact what happens is that your surface becomes much more smoother, and the reason is that you penalize much more strongly the points where the gradient is large. Okay, as I was saying, exactly the same situation as what happens in the fast diffusion case. So if you have a p which is large instead of a 2, you penalize much strongly the points where the gradient is large, right? And you observe this smoothing of your solution. So when you and we as analysts understand very well what's happening, because if you take the number of points in your data set to infinity, so if you pass from the discrete to the continuum, what you're basically trying to do is to minimize the p energy. So the LP norm of the gradient. And we know that the minimizer lives in W1P. So if P is large, then P may be, I mean, for P sufficiently large, P is going to be larger than dimension. And then by Sobolev embedding, by Morris inequality, you know that your W1P function is continuous, in fact, Holder continuous up to the boundary. You have a smooth boundary. So the boundary values are attained in a continuous way. Okay, and this is the reason why you obtain much better results in that case. So people started using the P Laplacian instead of using the Laplacian in problems of labeling. And of course, you see, I mean, this data points, this data is normally multidimensional, and the dimension is normally very large. So what you can do, in fact, is consider P very, very large, and you may as well consider P equals to infinity. And so this is also a natural way of seeing how the infinity Laplacian, that is my second example of a degenerate PDE, appear. So when P goes to infinity, you naturally obtain the infinity Laplacian. Of course, here, so what you are doing, instead of minimizing the P norm, you are minimizing the L infinity norm of the gradient. So you are in the context of the calculus of variations in L infinity. And so again, this degenerate PDE, the infinity Laplacian, appears in the so-called Lipschitz learning, which is the limit case of the P learning problem. And the infinity Laplacian, which is this highly degenerate equation here, appears also in connection with the tug-of-war games. This was a very interesting application of the infinity Laplacian, that people from probability found out. So the infinity Laplacian appears as the equation satisfied by the value of certain tug-of-war games, which are two-person zero-sum games, in which what one person wins corresponds to what the other person loses. And another application is optimal transportation. So it's an equation that appears in many contexts. Other examples of degenerate and singular equations are the porous medium equation, which is this PDE, where you see that now the equation degenerates not at points where the gradient vanishes, but at points where the solution itself vanishes. If m is positive, and if m is negative, then the equation is singular at points where the solution vanishes. Other examples are this doubly degenerate PDE, where you have a diffusion coefficient that vanishes at 2 points, say for example at 0 and 1, and this corresponds to the modeling of fluid mixtures, and also appears in chemotaxis when you consider the so-called what is it called, the prevention of overcrowding. So where your diffusion coefficient vanishes when the density is 0, and also when you attain a certain threshold, things stop diffusing to prevent overcrowding of the population. So you can normalize this and say that this coefficient vanishes at 0 and at 1, okay? And you have this double degenerate equation. And finally, and I'm going to speak in more detail about this, we have models of phase transitions, for example, the Stefan problem, where here you have the time derivative not of u, which you would have if this were to be the heat equation, but you have the time derivative of a certain maximal monotone graph, gamma of u, and this is why I have this inclusion here. So where basically this gamma is something like this. So it's a graph like this. It's a maximal monotone graph. And of course, the derivative at 0 of this gamma is going to be infinity. So you have a singularity here in the time derivative. So it's another instance where you have a singular equation. So given all these examples, what we want to do now is to try to understand what kind of regularity we can obtain for the solutions of these problems. And so basically the idea is to prove, say, continuity results. And we want to apply the iteration method of de Giorgi. So what we want to do is, for each point in our domain, we want to measure the oscillation in a box, or a cylinder, or a ball. I mean, it depends on the problem being elliptic or parabolic. I'm going to call it box in general. And what you want to do is to build a sequence of boxes that shrink to the point. You measure the oscillation on these boxes, and you show that as the boxes shrink to the point, the oscillation goes to 0. And if you can measure the way this oscillation goes to 0, you derive a modulus of continuity. So this is the schematics of what I am saying. So here we consider space x, and here this is time. So of course here x is one-dimensional, but I mean you can think of a ball in x, and then so you have a cylinder. And so what you want to do is this: you want to prove the continuity at this point. You build this sequence of boxes, you measure the oscillation, and you show that when you go from one box to the other, the oscillation decreases, and you want to show that it goes to 0 when these boxes shrink to the point. Now, the basic idea to do this is to use the Georgi-Nash-Moser theory. And so at the basis of this method, you have what's called the Choppy estimates. So which are sort of energy estimates that you obtain from your PDE. And in the classical case of a linear elliptic equation, the Choppy estimates look like this. So let's not worry much about how we derive these estimates. The only point I want to stress is that here you have power 2, and here you also have power 2. So these are kind of reverse Poincare inequalities when you control the L2 norm of the gradient using the L2 norm of the function. But my point here is that in the classical case of the Georgi and Nash, the power that appears on the left and on the right is the same, is power 2. So when you go from the Laplace equation, or say a general elliptic equation, to the degenerate case of the P Laplace equation, what happens is that if you write the Choppy estimates, the only difference basically is that you replace the 2 by a P. So the degeneracy is not really a problem in the elliptic case, because you somehow conserve the homogeneity in your Choppy estimates. And this allows you to apply the same method. And this was immediately understood after the Georgi and Nash by the Russian school of Vladizhenskaya and Guraltseva. And so for weak solutions of the P Laplace equation in the elliptic case, you can also prove that solutions are Holder continuous, just as was already known for the case of the elliptic equation, the linear elliptic equation. Now, when you go from the elliptic to the parabolic, what happens is this. If you have the linear principal parts, as before, you see that you obtain now Choppy estimates. So this is, say, the elliptic parts that we had before. And now we have 3 terms coming from estimating the time derivatives. And here you see that they all have the power 2. So you have the same power everywhere. So everything is homogeneous, and you can still do the same type of analysis and prove that solutions are Holder continuous. Now, when you have the principal part with the P Laplacian, so when you have the parabolic P Laplacian, things start to do not work. And what happens is that, of course, when you have the principal parts, you have the elliptic estimate here with power P, as we had before. So this is exactly what we had here, okay, coming from the principal part. But then from the time derivative, you get the same 3 terms with the power 2. And now you lose the homogeneity. So now you have power 2 and power P. And unless P is 2, these are going to be different, of course. So note that what goes wrong here is not the fact that this is nonlinear, because, I mean, this can also be nonlinear. Okay, this can be nonlinear. The important thing here is that the principal part grows linearly with the gradient, so that you have power 2 here. So it's not the linearity that's important. You know, the Georgi-Nash-Moser is not a linear theory. I mean, it was done for linear equations, but the linearity doesn't play any role. The important thing for this to be homogeneous is that the principal part grows linearly with the gradient. So when the growth is nonlinear, like here, the principal part grows like the power P minus 1 of the gradient, then the Choppy estimates become inhomogeneous, and you have a problem, and the method does not work. So we have to try to make everything homogeneous again. So to try to understand what you have to do, let's compare the P-Laplace equation with this equation, which is called sometimes Schrödinger's equation. And this one is homogeneous. Okay, so you see, if you replace here u by lambda u, you get a solution of the equation, right? Because this comes out with lambda to the p minus 1, and here lambda to the p minus 2 plus lambda, which is lambda to the p minus 1. So this equation is homogeneous, so in principle everything should work for this one. How do we compare Schrödinger's equation with the P-Laplace equation? So here I rewrote the P-Laplace equation in this form. You see that if I take this derivative here, what do I get? So this thing here is going to be p minus 1 u to the p minus 2 dtu. And so this u to the p minus 2 cancels with this u to the 2 minus p. And if I choose the constant in the right way, this constant 1 over this constant to the 2 minus p cancels p minus 1, right? So in fact, when I multiply this factor by this derivative, I get just the time derivative of u. And this is exactly what I have here, is exactly the P-Laplace equation. Okay, so this is the P-Laplace equation. So what I was saying is that all this, in fact, is dtu. And now, how do we compare this with this? So of course, the principal part is the same. And here we have the time derivative of u to the p minus 1, but we have a factor. And this is what we want to get rid of. So if we could get rid of this factor, we would have Schrödinger's equation, everything would be homogeneous and we would be fine. But of course, we can not just discard this factor, right? So what is the idea? The idea is the following. So the analysis is typically done in boxes that reflect the natural homogeneity of the PDE. So for the P-Laplace equation, you would scale like r in space and r to the p in time, right? This is what you would expect. But if you do the analysis in boxes like this, things do not work. So what we have to do is to somehow stretch these boxes and do the analysis in boxes of the form r in space, a0 r to the p in time. So the time length of this box must be stretched according to a factor, a0, and this a0 has exactly this form. So what do we do? So what we do is this: we start with a box. So when we do this analysis, this oscillation reduction, we start with a box, with a large box, which is this dotted box q r square r. Okay, so r in space, r square in time. So r is typically a small number, so don't be surprised that r squared is much larger than r to the p for p greater than 2. Okay, so we start with a box like this contained in our domain, and we measure the oscillation of a solution in this box, which is the difference between the supremum and the infimum on the box. Okay, and then we rescale the r to the p box according to a factor which has exactly this form. So it's the oscillation that we measured in this box divided by a constant, which is something universal, depending only on the data, to the power 2 minus p. So you see that this number in principle is a large number because the oscillation is small. This is going to be large, so this is going to be very small. So since p is greater than 2, so I'm considering the case p greater than 2 here. So this is a small number, so this is negative, so this is going to be large, right? Greater than 1. So we are in fact stretching the box. And if you compare this factor that you use here to stretch the box with the factor that we want to get rid of, let me erase this thing. Why can't I erase this? Well, I don't know. Okay. So if we compare this factor here, so it's the solution divided by a constant to the 2 minus p, with this, which is the oscillation of the solution divided by a constant to the 2 minus p, you see that there is a strong similarity, right? But I mean, I could not get rid of the other factor in PDE, of course, but I can multiply my cylinder by this constant and stretch it according to it. Now, the idea is that if I rewrite my Choppy estimates over these enlarged boxes, then I recover the homogeneity. So somehow the geometry of the problem absorbs the degeneracy in the equation. So let's see why that happens. So the traveling term would be this one, where you have the 2 and the p. Okay, so let's try to transform this 2 into a p. So I have a square here. I'm going to write this as power 2 minus p multiplied by power p. Of course, this cancels this. This is just the square. So we have equality here. That's obvious. So now I have the power p that I want. I'm going to keep it here. So now let's look at this factor here. So typically we are doing this. So these Choppy estimates are estimates on level sets, which involve the positive part of the difference between u and a certain constant. And typically this constant is of this form. So it's the supremum minus the oscillation divided by a large number. Okay. So if k looks like this, the positive part of u minus k is going to be either 0 if this is less than 0, if this is negative, or it's going to be exactly u minus k. So, and if k looks like this, u minus k is going to be u minus this plus this, okay? So exactly what's written over here. And since this is the supremum, u minus the supremum is going to be negative. So this sum is going to be less or equal than the oscillation divided by this constant, right? So here, since this is taken to the power 2 minus p, which is negative, if this is less or equal than this to the power 2 minus p is going to be greater or equal than this to the power 2 minus p, which is exactly what I wrote over here. But this to the power 2 minus p is precisely the A0. So the square of this positive part of this difference is the p, the power p of this positive part of the difference multiplied by, well, it's greater or equal than this multiplied by this constant. So if I replace here the 2 by the p, I just have to pay the price of writing A0 over there. All right. And this is probably what I'm doing here exactly. So now I have the p. Okay. You see that this term is on the left-hand side, so I can bound it from below, right? I pay the price of this A0 here, and I replace the 2 by the p. Now I divide by A0. So I take it out of here, and here it appears 1 over A0, and the same on the right-hand side, but I'm not writing it. And what happens now is that by a simple change of variables, so you see that here, this is just an integral in space. This is an integral in space and time. So if I do a change in the time variable, I rewrite this term in the rescaled box, and the A0 just disappears. And I get homogeneous estimates written over the new rescaled boxes, right? And I call this intrinsic because you see the factor that I use depends on the solution itself. So it's intrinsic to the solution. And at each step, I have to do this. I have to rescale according to the oscillation in the previous box, okay? So, as I said before, intrinsic geometry absorbs the degeneracy in the PE, right? And roughly speaking, we can say that the equation behaves in its own geometry like the heat equation. Okay, so this is the essential idea behind this method of intrinsic scaling which was invented by Emanuele Di Benedetto. And I mean, of course, the technical aspects of the method are quite intricate. And if you're interested in these things, I think a right place to start is my book about the method, which on the first part contains an introduction and an explanation of these ideas with all the technical details carefully, I hope, written down. And then on the second part has some applications of the method to some applied problems, one of which I'm going to talk about right after. So also, if you're interested, I'm planning to give a short course very soon at UFPB. So if you're interested, you might want to follow the mini course that I'll be teaching at some point in this coming Brazilian summer. Okay. So now let's go back to the Stefan problem and to see. Let me talk about a little bit about quantitative estimates. So the method of intrinsic scaling produces qualitative information, saying that you obtain that solutions are Holder continuous for a certain power alpha. You have absolutely no control on the size of this alpha. And let me now talk a little bit about quantitative estimates. So the Stefan problem, as I said, is a simple model for a phase transition at constant temperature. So let me briefly explain the physics. So suppose you have a unit mass of ice, for example, and you give energy to this unit mass, this little cube of ice. And what happens is that as you give energy to the system, you see that the temperature goes up, of course, until you reach, say, 0. And then if you continue to give energy to the system, you see that the temperature remains at 0 for a while, and only after a certain amount of energy is given to the system, it starts going up again. So this amount of energy, this L here, that you must give the system to go from ice to water is what we call the latent heat of the phase transition. And now if you invert this function, you obtain here this relation between energy as a function of the temperature, which is what we call a maximum monotone graph. This is no longer a function, so it's a maximum monotone graph, because here you have a graph, you don't have a function. I mean, the 0 has to 0 corresponds all this segment here. Now, the right way to formulate weakly this problem is to consider the following PDE, where you don't have the heat equation. Say, suppose now that P equals 2, so here you have the Laplacian, and here you don't have the time derivative of U, you don't have the time derivative of the temperature, but you have the time derivative of V, which is a choice in this maximum monotone graph. So this is the right way to formulate the problem, okay? Where V is the identity plus L times the Heaviside graph. Okay, so this is typically the identity, and then you have the Heaviside graph, this graph, times L. Okay, so here you have the identity, here you have the interval 0L, and here you have the identity plus L. Okay, so you see, suppose you have a nonlinear diffusion and you have the P Laplacian in the principal part. You see that your equation is degenerate in the principal part because P is greater than 2 again, and you have a singularity in the time part because this gamma has a derivative at 0, which roughly speaking is infinity, right? Because of this jump at 0. So you have a PDE which is degenerate and singular at the same time. And so you can show still in this case that solutions are continuous. What do you do? So here, basically what you do is this. You regularize the maximum monotone graph like this. So you consider a regularization. So this is what I call here gamma epsilon. you see that you obtain these bounds for the derivative, right? So the derivative is greater or equal than 1 and less or equal than 1 plus L to the epsilon. So you see as epsilon goes to 0, this upper bound goes to infinity. So you lose something when epsilon goes to 0. But what you have to show is that your sequence of approximate solutions corresponding for each epsilon is uniformly bounded and equicontinuous. If you can prove this, then you can obtain continuity in the limit, right? You don't obtain Holder continuity, but you still obtain continuity by Ascoli's theorem. So what happens in this case? So if you look again at the Choppy estimates, what you observe in this case, because you need to obtain estimates that are uniform in epsilon, otherwise you do not prove equicontinuity. Of course, you can obtain estimates with power 2 here if these constants depend on epsilon, right? Because you can use this bound. But I mean, they depend on epsilon in the wrong way, because when epsilon goes to 0, this goes to infinity. So if you want to obtain estimates which are uniform in epsilon and allow you to pass to the limit, to carry information all the way to the limit, you need these constants to be independent of epsilon. And the way to do that, the price you have to pay to obtain constants that do not depend on epsilon is to obtain here power 1. I mean, I don't have time to explain why with power 1 you obtain uniform estimates, but believe me that in order for these estimates to be independent of epsilon, for these constants to be independent of epsilon, you need to put power p here. So now you have power 2, power p, and power 1, and you have to make all these compatible. So it's like this. So at the level of the analysis, you get a power p in your estimates, and this corresponds to the degeneracy in the PDE, and this comes from the fact that the physics of your problem involve a nonlinear diffusion in the principal part. On the other hand, the one that you see here at the analytical level corresponds to the singularity in the PDE. It comes from estimating the time derivative, which has a singularity, and this is coming from the fact that you're modeling a phase transition. So you see, I mean, I like to look at the analytical level and see that this P comes from the physics. So this for me is a nonlinear diffusion. This is a phase transition. If everything is 2, you just have the heat equation. You have linear diffusion, you don't have a phase transition. But when you have nonlinear diffusion and you have phase transition, you immediately have this non-homogeneity corresponding to the fact that your PDE modeling the phenomena is degenerate and singular at the same time, okay? And so what can we do? We can still show that solutions are continuous. This is something that can be done. So by paying this price, you use intrinsic scaling in the right way, and you can apply the method and show that solutions are continuous. And then, but you lose Holder continuity in the limit, right? So you have Holder continuity when you have the power 2 here. The price that you have to pay to have homogeneous estimates is that these two 2's become 1's. And so you lose the Holder continuity. You still prove that solutions are continuous. So the temperature is still continuous in the Stefan problem, but you lose the Holder continuity. And then you may want to ask, what is the modulus of continuity? What is the modulus of continuity? And what was known until some years ago was from the late 1970s, early 1980s. So in the one phase case, so when you don't have PDE on the ice, so you just have that U is less or equal than 0. When you don't have, so for the one phase problem, the modulus of continuity that was known was this one. And this was by Caffarelli and Friedman. So log of 1 over r to a certain power. For the two-phase problem that we are trying to model here, the state of the art was obtained independently by Di Benedetto and Caffarelli and Evans, and the models of continuity looks like this, where you have two iterations of the log, and then you have minus sigma for some sigma which was not known. So the proof of Di Benedetto was more general. It allowed general structures in the principal part, but always growing linearly with the gradient, and also allowed lower order terms. The proof by Caffarelli and Evans was more a typical Laplacian proof. So it was obtained for the case where the principal part is the Laplacian. It involved the green formulas and so on. So it was not immediately generalized. So, and I don't think I'm going to have time to speak about other problems because we are almost at the limit. But together with Paolo Baroni from Parma and Tuomo Cusi from Helsinki, we improved these models of continuity in 3 ways. So this was published in ARMA for the interior case and was extended in CIMA for the regularity up to the boundary. And what we proved was that, in fact, the modulus, as in the two-phase case, as exactly the aspect of the modulus that was obtained by Caffarelli and Friedman for the one-phase problem. And so the improvement is threefold because, first of all, our result holds for any p greater or equal than 2. So we covered the case of nonlinear diffusion, so the case where the principal part does not grow linearly with the gradient. But most importantly, even if p equals 2, we got rid of one iteration of the log. So we got rid of one iteration of the log, and we gave an explicit expression to this constant here. So the constant was only known to be a positive number. We've shown that this constant is exactly p divided by n plus p. Okay, so threefold improvement. It holds for every p. For the degenerate case, we got rid of one iteration of the log, and we have derived exactly the expression of the constant. So this is a quantitative result. Of course, we don't know if this is optimal. I mean, we would have to have a counterexample, but we believe this is pretty much the optimal models of continuity. This has been recently extended by other people, for example, to cover the case p less than 2, so the singular case, and also other types of boundary conditions that we did not consider in our paper. Okay, thank you very much.